So today I'm going to start, we are going to end the discussion on neural networks. So what we are going to, what we ended last time was we were trying to derive the gradient of the error function with respect to all of our weights so that we can then feed it into the optimization function or the minimization, like the gradient descent routine, which will help us get the weights which give you the minimum error, right? So again, remember said that there is a notion of an error that we have already established for our neural network, right? So the error looks like this. So in today's discussion, I'm going to assume that we have only one data point, all right, one training example. And that is why the error that we compute, we do not have another subscript there. But if you have many training examples, then all you do in this error is that you put another summation on the top, right? So this is an error for one training example in which the true label is y of L. Sorry, the true label is y and the output is O, and then you compute the error like this. But in general, in the assignment description, we compute the total error, all right, which will just be another summation over here. The reason I don't have it here is because otherwise I had to put subscripts here, and that becomes a little more cumbersome to sort of go through, all right? So we know the gradient descent algorithm. This is our error, and all of our weights are our parameters that we want to optimize on, which means that we need to compute the gradient of this error with respect to all of these weights that we have, right? So we have, so let's just go over the architecture again of the neural network. We have weights at every hidden node, right? We have m+1 nodes, so we'll have m+1 weight vectors over there. And then we also have k output nodes, so we will have k, we have m hidden vectors over here and k here. So total we have m plus k hidden, m+1 weight vectors, and we need to compute the gradient of this j, which is our error function, with respect to all of these, all right? So we can also simplify it, which means that we can compute the gradient, because these all are independent of each other, right? So we can compute the gradient of j with respect to each of these weight vectors separately, and then just update them in the gradient descent until we converge, right? And then we can simplify it even further, is that these weight vectors, right? Each weight vector is a vector, some bit vector, right? So you can compute the derivative of this j with respect to each one of those bit vectors and essentially update them. So I'm going to explain it to you in a way that helps you understand the assignment a little more. So what we do is, at a hidden node, right, at a hidden unit, we have a weight vector which we typically, I'm going to denote it with a small bold of W. The reason I use a bold is because it's a vector, and I'm going to put a superscript of 1 to indicate that this is a hidden unit, right? And then there could be many hidden units. There could be m hidden units. So we are going to use the subscript j to indicate the jth hidden unit in this layer, right? So this is actually a vector, right? And this will have d+1 entries in it because it needs to combine the d+1 inputs coming from the input layer, right? So you can think of this as w of 1 j1, w of 1 j2, and so on until w of wjm1, right? So these are the, so each one of these is a scalar value. This is a number, right? And we put all of them into a vector, right? What to make it easy to implement this algorithm, what we typically do is we put all of these vectors. So j goes from 1 through m, because there are m hidden units in which you have weight vectors, right? So we put all of these in a sort of a matrix, and we call that a big W of 1. Okay, so in this, each row here corresponds to the small one. So this will be 1, and this will be the second one, and so on. This would be the jth one, and this would be the mth one, right? So we essentially construct this matrix. This has nothing to do with backpropagation, really, but this is more to keep our uh, to make our programming a little easier. Okay, so we maintain a matrix like that, and the same way at an output unit, we have a vector there as well, and we are going to represent it as a bold W superscript 2 to indicate it's at the output layer. And then I'm going to use L, I think, L to indicate something that. And this is also a vector, right, with m+1 entries in it, because it needs to take input from m+1 hidden units and combine them. And then this L goes from 1 through k, if you have k output classes, possible classes. So what we do here is we represent this as another matrix, W of 2, okay? And again, this is the same thing. Each row, this will be W1 of 2, W2 of 2, WL of 2, and this would be WK of 2. Each row is a weight vector associated with the LS output unit, right? So this, we are going to use these in the assignment. So these are essentially our parameters of this model, right? These are the weights that we want to compute, which means that we want to compute the gradient of J with respect to all of these weights, all right? So what we typically do is we compute the gradient of this, so the gradient of this J with respect to all of these weights can be computed by computing the gradient or the derivative of J with respect to each one of these entries in these matrices. So if you put all of these matrix entries into one long vector, then all you need to do is compute, so you want to compute the derivative of J with respect to 1, 1, 1. So basically, I start from here, let's say, right? So derivative of J with respect to this entry, derivative of J with respect to this entry, and then we keep going on, and then at some point you would do all of the first ones, and then you start with the second matrix, say derivative of J with respect to the first entry in the second matrix, and so on, right? So this is what we need to compute. If we can compute this, then we can do the gradient descent very easily, right? Because after that, all we will do is we will say that any entry here, let's say W1 of 1, will essentially be the old value of this minus eta times the derivative of this with respect to the derivative of the error with respect to that weight. All right. So what we are going to do today is we are going to compute these values. Okay, and we are going to compute these values, and then everything else falls into place. After, yes, go ahead. It doesn't matter, but you have to be careful after that, because once you get the gradient, when you put them back, you need to remember that you took them as columns. So it doesn't really matter. Yeah. In these matrices, so that's easy, right? So this is the hidden matrix, right? In this, the number of columns here would be d+1, because this vector takes the inputs from the input layer, right? So there are d+1 inputs coming from the input layer. If you don't include the bias in D, right? So that d+1, and this one is m+1, because there are m layers and then there's a bias node. So when you combine them, right? There was a question here. Okay, all right. So let's keep going. So today, what I'm going to do is I'm going to show you how to compute the derivative of any entry in this matrix, any general entry in this matrix, and the derivative of J with respect to any entry in this general matrix, right? So if we can compute that, essentially then we'll get the derivative with respect to every entry, and then you can apply the gradient descent, all right? In the assignment, and probably, I don't know if the TA went through that in the recitation, but for the assignment, you do not have to implement the gradient descent, okay? You will use a library in Python called scipy.optimize in which there is already a function called gradient descent. All right. All it needs is the objective function and the gradient. All right. So you will write a function which computes this and which computes the j, of course, and then just feed it to your that function, and it will optimize it for that. The reason we do that is we could have used our own gradient descent algorithm, but that scipy.optimize one does something a little more smarter. So it works faster than if we had implemented our own. So essentially, it's not like a dumb gradient descent. It is adaptive. So the steps that it takes kind of takes into account how far you are and everything. So you don't have to worry about that part. So for you, all you need to do is implement a function that computes the objective function and your gradient with respect to all of your weights. And if it is correct, then your that function will take it and spit out the minimum value. All right. Any questions so far? Okay. So today what we are going to do is we are going to see how to compute d of j with respect to a general entry in this matrix. Let's say any entry Lj, right? So so in the lth row, the jth column. So we're going to compute that, and we will see how to compute in this matrix any entry here. Let's call it ji. All right. So we are using j to iterate over the hidden units. We are using L to iterate over the output units, and we are using I to iterate over the hidden units. All right. So we're going to see how to compute that. All right. Any questions so far? So this is going to be a little what should I say? It becomes hard to follow at times because there's a lot of notation. So bear through it, and then when you go back, please follow it again, and please do the gradients homework as well, and that way you will have a little better understanding. So here I have drawn a sample network. Okay, so we're going to look at this one. So let's assume that our d is 4, so our d plus 1 is 4, and our m plus 1 is 5, right? And then we can generalize it, and let's say our k is 3. That means there are 3 output classes, there are total 5 hidden layers, and there are 4 inputs, including the bias term, right? So you would have connections everywhere. So I've just simplified it. I've only connected some of the nodes, right? So the first thing you need to see is that your input, right? Your input will be a vector x, which will be essentially a vector with 4 entries, 4 elements, which is these, right? These get fed into the input layer. These get fed as the input layer, right? Then they go to the hidden layer. And then we also have the y. Y is the true label because this is training data, right? Now, y in general could be either 1 or 2 or 3, because it could be one of the 3 classes, right? It could be 1, 2, or 3, or it could be red, blue, green. It could be sunny, rainy, cloudy, whatever output it is, right? But what we do is to make it a little more mathematically easier to process, we convert this into a bit vector. We convert this into a k-bit vector. In this case, k is 3, so 3-bit vector. And depending on what the value of y is, we will make one of them 1. So let's say y was 2, right? So we'll make this 1 and everything else as 0. So this is also known as 1 of k encoding, right? This is general term, very easy. In data mining, they use it a lot. In statistics as well. So essentially, you are converting a categorical or basically a category into a vector, right? A numerical vector. So now what happens is that your true labels, so essentially you have these true labels, y1, so you can think of this as y1, y2, and y3. So this will be y1, y2, and y3. So this is the true label that you have, right? Now we went through the forward pass of of neural networks last time. So what happens is this x goes here, all the entries go to all the hidden units. They get combined using a vector here, right? So this is going to do W1 transpose X, and then so on. and they produce an output, then that gets fed into the sigmoid function. So, and then that sigmoid output goes into all of the output units, and at the end that gets fed into these these output units. You do a W transpose X here. Well, instead of X, it will be the output coming out, and then that gets a sigmoid on it, and that gives you O1, O2, and O3, three numbers, right? So what you do now is you compute the difference between these. I'm showing you how to do the error, right? So you compute Y1 minus O1, Y2 minus O2, and Y3 minus O3. You do a square of that, right? And then you sum it up. So that is your error, right? So your error is summation YL minus OL whole square. And you also put a half here, L equal to 1 through K, right? So that is your error. Okay, so now we need to know how to compute the gradient of the derivative of this with respect to any weight vector entry here, right? So let us consider the LS output unit. All right, so which is over here, right? So LS output unit would have a vector associated with it called this. This would be a m+1 length vector, which will have entries that we are going to call WL1, WL2, WLJ, something. WLm+1, right? So this is the vector, right? So now let's look at right. So now we need to compute the d by d of j with respect to any one of these, d of WL of j of 2, right? So now let's look. So if you see this equation, you do not see WLJ here, right? So it's not there explicitly, right? But what you know is this O of L has been computed by using all of these W vectors, right? So all we need to do is get that relationship. So you can say that this can be written as, so because WL of j gets combined to compute this what we call net of L, right? So here at each entry, what's happening here is that this we call the net function, and this we call the output of this function, right? So we can call this as d of net of L. So this is just the derivative chain rule. Okay. Now net of L is connected to J like this. All right, so let me just draw a little diagram here so that you don't get confused, right? So what's happening at the jth at the lth output unit is that there are some inputs coming to it, right, from the hidden layer, right? Let's call them z's, from z1, z2, and we'll see what they are eventually. So there are z m+1 inputs coming in from m+1 hidden layers, right? And here all of them are getting multiplied with WL of 1, WL of 2 till WL of m+1, right? And that dot product, we call that as net of L. That's net of L is essentially WL transpose Z vector, whatever Z is coming, right? This can also be written as a summation of J equal to 1 through m+1 W L of j times z of j. All right. So this is essentially the dot product that is coming in at the lth output unit, right? So this is net of L, right? And then we compute the O of L is essentially the sigmoid of net of L. right? That's the output. So what I have done is, because O of L is directly connected to J, so I first compute the derivative of J with respect to O of L, then compute the derivative of O of L with respect to net of L, and then compute the derivative of net of L with respect to this, just to keep it, just to make it directly related, all right? So that is sort of a simple setting. So now we need to compute what are these entries, right? So, so let's do them one by one. So this is the first entry that we need to compute. This is the second quantity, and this is the third quantity. All right. So what is d of j by d of OL, right? So remember, j is nothing but this summation, right? So j is, so we have to compute d of O of L half times L equal to 1 through k y of L minus O of L whole square, right? Now, this is a summation, but only one entry in that summation depends on O of L. All the other ones do not, right? So when you open this summation and you move this derivative inside, a lot of them will become 0. So the only thing that will be left is half d of O of L times y of L minus O of L whole square, right? Which can be written as minus y of L minus O of L. All right, because it's 2 goes cancel with this 2, and that's left. Any questions so far? All right, good. So this is, so we have computed the first quantity here. Then the second question comes, what is d of O of L over d of net of L? Now remember that O of L is just a sigmoid of net of L, right? So it is d of net of L times the sigmoid of net of L. Now here is where you will appreciate the sort of the simplifying value of sigmoid function. Okay, so we'll have a little sidebar here. So if you have the sigmoid of any function, of any argument, let's say a, right? So if you need to compute d of sigmoid of a, right? It gets very simple, because sigmoid of a is essentially d of a 1 over 1 plus e power minus a, right? So if you compute the sigmoid like this, what it will give you is, it actually becomes square and then e power minus a, right? Which is, if you simplify it, times 1 over 1 plus e power minus a, which you can write as, actually you can write it as sigmoid of a times 1 minus sigmoid of a. All right, so that's just a property of a sigmoid function. There's nothing to it really, right? But that lets us write it in a very simple way, which means that this is nothing but sigmoid of net of L times 1 minus sigmoid of net of L, and sigmoid of net of L is actually OL, right? So I'm just going to write it as OL times 1 over 1 minus OL. All right, so this is the second result. Then we need the third. Third is this thing, right? So what is d of net of L by d of WLJ2? Little higher, like this. All right. Okay. So we need to compute this. Now, because I remember that I wrote this net of L is basically this summation, right? So I'll put that here. 2 times summation j equal to 1 through m plus 1 WLJ to ZJ. Okay, remember ZJ is the input that is coming from the jth hidden node, right? Which you would have already computed when you were doing the forward pass. So you have that, right? So if you compute the derivative of this summation, you will see that only one entry in this summation depends on this. Everything else is independent of that. So they will become 0. So this will essentially be ZJ. Okay. So now we have all the three values. So which means combining, yes. Oh, it's okay. So Zj is, this is a output unit, right? So it is getting inputs from the hidden layer. So there are m plus 1 hidden layers. So all the inputs from the hidden layer are, we call them Zj. Okay. These are, and we'll come to that. Zj is basically the sigmoid of the W transpose of X over there, right? So you have that. When you did the forward pass, you would have computed all of these. So in your code, don't like delete it. You need it in the backpropagation. Combining 1, 2, and 3. Well, let me call this 3. This is 2, and this is 1. We get dj of d of lj of the second layer is minus, right, yl minus ol times ol times 1 minus ol times z of j. All right. So this is the derivative of j with respect to any weight entry in this big matrix. So remember, I'm just gonna sneak this in here. So remember, we are trying to find the derivative of j with respect to each entries in both these matrices, right? So far what we have done is we have the ability to compute the derivative of j with respect to each one of these entries, all right? And now we will see how to compute it further, all right? So in oftentimes what we do is we denote this as delta L, okay? Just because we didn't have enough variables flying around, so we introduce one more. And so this is typically we call the error. Yes, go ahead. Why does J have only one index? Right. So every hidden node is producing only one output, right? So that means that m plus 1 hidden nodes will produce m plus 1 outputs. So that's why. So there will only be z1 through zm plus 1. These are all scalars. Any other questions so far? Beautiful. All right. So we have computed this. You will see why I use this. But typically we call this as the error at lth output. So in the gradients problem, when I talk about the error at lth output, this is the error, right? Delta L times whatever input that is coming in, okay? This part was easy, okay? Why? Because the weights at the output layer, where's my output layer? So the weights at the output layer are directly connected to O's, right? And that is why I can compute the gradient in a very easy way, if you call this easy. But when we have to compute the gradient of this error with respect to the weight entries over here, that becomes a little more cumbersome. Why? Because all of these weight entries are producing the ZJs, and these ZJs are going to all of the outputs, right? Which means that it's a little more cumbersome. So essentially what happens is that now what we will do is we will propagate the error that we calculated at the output layer back to the hidden layer, all right? And then compute the derivative of that error with respect to each one of these hidden units. That's why it is called the backpropagation algorithm, right? So first we go forward, then we come backwards, right? So if you become too adventurous and say, I'm going to add more layers, right? I'm going to add more hidden layers now. All you need to do then is basically first do the forward pass and then do the backpropagation, right? So conceptually it's easy. Implementation wise it does become a nightmare at times, right? But conceptually that's the easy way to understand it, the backpropagation. All right. So now let's look at, so we have done this part. So I'm going to use a new sheet now. Right? So now we'll say, let us consider the jth hidden unit. right? So the jth hidden unit is represented as Vj, right? Oh, sorry, J. And you can write it as a vector with entries J1 all the way to, and there will be, let's call a jith entry, and then at the end there will be d plus 1th entry, right? So we are going to consider one of these entries and compute the gradient of that, right? A derivative of that. Any questions so far? All right. Okay. So now if you see this, right? So we need to compute d of j with respect to 1 ji, right? So any one entry here, right? Now remember, now this becomes a little tricky, right? Because j is not directly connected to these, right? So what happens is that the way you write this is that this would be d of net of j. So let's say net of j is that W transpose thing, right? And then net of j with respect to the output going out of this, which is zj, right? So zj, and then of the error with respect to z of j. All right. And this can be written as, just trying to, yeah. This is a layer number, right? So 1 means it's the hidden layer. 2 means it was the, because here we were doing all 2. That's the output layer. The reason I say 1, 2 is because in principle you can have many hidden layers. So then you would number them like that. But here we are just using hidden and output like that. Okay. All right. So this actually can be written as, and this is where I'm not going to spend more time here, but I just want to give you the general sketch. So this stays because this is inside the unit, and this one can be written as d of j, the net of L net of j. Okay, so net of L is the net output that's happening at the output layer. Yeah, I'm sorry. Oh yeah. Oh, this. Right. You're right. Well, this should be net of j, right? Okay. Well, for now I'm going to just cancel it. All right. Let's just look at this one, right? So you can go back and sort of understand. It takes too long to really explain it. But the idea here is that the way you want to understand this is, where's my network? So you're trying to compute the derivative of this error, which is here, with respect to a weight vector over here, right? The effect of a weight vector gets split to all of your output units, right? Yes, go ahead. You mean in here? So this is the, okay. So 1 here means that we are talking about a weight vector at a hidden unit, hidden layer. Sorry, a hidden layer, right? This is the jth unit in the hidden layer. Okay, j will go from 1 through m, and then each vector is essentially a vector, so it has many entries in that. So we use this second one to iterate over the entries.
Here's my question, but each J unit essentially is a linear combination of all the W transpose X.
Right.
Well, eventually here we are scalar.
Yeah.
Then Y is a vector, and then should be a scalar.
No. When you compute the this transpose X, that will be a scalar. Right, but I'm just listing this vector right now, right? Because we need to compute the derivative of j with respect to each one of these entries, right? And then this comes. So I'm going to leave this here, right? And if you go through the notes, you'll see how math works out there. But the basic idea, the reason I have summation over here is because each one of these weights impact each zj's over here, and that zj goes to every one of these output units. So which means that this entry over here will affect each one of these O's, right? So when you compute the derivative of this error, it will have a summation here, because you need to compute the derivative of the effect on all of the outputs. Okay, so just to close it, I'm going to write the final result, but please make sure that you sort of go through this at home as well. This actually looks like minus OJ 1 minus OJ summation L equal to 1 through K delta L. Remember that delta L from the past. WL of J this is W1, the second layer, times X. This is the input that is coming in, remember, I. All right, so this is dj over dwj of I. The first in the input layer is this much. Okay, so you can see that you computed some error delta L at the output layers, right? And now you are propagating it back. So sometimes we also write it as minus delta J xi, where delta J is the error at the hidden unit, and that is written as OJ 1 minus OJ summation L equal to 1 through K delta L WLJ 2. All right, so these are the derivations for the error, right? So in your assignment, or in general, when you go out and try to implement your own neural network, these are the things that you need to compute to do the backpropagation. After this point, what happens is you feed this to your gradient descent and it will find the minimum. Any questions so far? All right, fantastic. Another point I wanted to make was that this error function, there's nothing sanctimonious about this error function. Okay, you can have any other error function. In fact, in last year's assignment, we gave a different error function, which means that your derivations will change a little bit, because depending on what. So in last year's assignment, I think the error function looked like this. It was YL log of OL times plus 1 minus YL log of OL, 1 minus OL. So it looked like this. So it was slightly different, right? So which means that when you compute these gradients, your derivations will change. So in general, when you go out and say, I don't want to use this error function, I want to use something else, the general philosophy would be the same, except that your derivations will change a little bit. And the same thing goes for the choice of the sigmoid function. So in neural networks, there are other commonly used activation functions as well, besides the sigmoid. So sigmoid is one, but people also use something called a tan-h, which is just a different mathematical function. So if you use a different function in the unit, then your derivations will change again. So instead of okay, so instead of using this, right, this would change to something else. So that's how you sort of generalize the neural network to other settings. Any questions so far? All right, so let's move on. We have 10 minutes. So far, I have shown you how to use a neural network and how to train it, right? So let's sort of wrap up our discussion. So all of this is there. So if you can sort of figure that out. So this is the final algorithm, right? So final algorithm is that in your learning, in your backpropagation, first you move forward, you compute your ZJs and OLs, then you compute the errors and move back, and then you update your weights according to this equation. Where is the equation? Here, right? So these are our update rules, which is standard gradient descent rules. All right. Uh, so just to conclude, right? A lot of times what happens now, this error function is a pretty, yes, you had a question?
Yeah, error that you have on the previous slide, the same as the lambda.
Lambda from the gradient quiz? Yeah, that's the same. It's lambda, right? Okay. Right. So another point about gradient descent, also about backpropagation, is that this error function is pretty complex, right? So there are no guarantees that it is a convex function, which means that it might run into local minima issues, right? It's sort of weird shape. So there are no real guarantees of convergence. In fact, when you will do your assignment, you will see that sometimes it takes very long, because depending on where you started from, you could reach to a local minima, or it might get stuck somewhere. So there are no guarantees of convergence. Sorry. But oftentimes what happens is that that's not really a big issue. You can stop at some time. You'll say, okay, run it for 200 iterations, whatever you get. Oftentimes that's good enough, all right? But there are no guarantees. Then there are several extensions to backpropagation, and we are not going to talk about them too much. But there are techniques like adding momentum. Momentum means that what is momentum again? So if you are sort of updating your weights, sometimes you when in the new iteration, you maybe do not change, you do not budge from your original position too much, so you have some inertia to yourself, right? So those are some ways to make sure that you do not move around in wrong directions. You can also implement a stochastic gradient descent version, right? So we saw stochastic gradient descent earlier, and it works in a very similar way, because you can compute error with respect to only one training example and then keep updating that and then take the next example. So there are ways to extend that as well. All right, so this kind of brings us to the end of neural, well, not quite, but just the implementation details you should be comfortable with. When you go back, you can look at it a little more, all right? So I'm now going to talk about very important concept in general machine learning in the context of neural networks, which is called a bias-variance trade-off, right? This is true for any machine learning algorithm, but it's easy to explain it now since you understand neural networks, all right? So in general, neural networks are what we call universal function approximators, which means that your data could be of any complex shape. By shape, I mean that, let's say you're trying to distinguish between three types of points. Whatever the surface there could be, you can learn or you can come up with a neural network that will learn that surface, okay? So that way we call it a universal function approximator, because you assume that that function defines that surface, so your neural network can approximate that function, all right? However, and that you can do by making your model more complex, which means you can add more layers or add more units per layer and do that. But the question is, do you really want to do that, all right? And that's where this important notion comes in. So the question is the model which gives you the least training error the best model, right? So let me give you an example over here. By the way, when I post these scans, right, what I do is I keep appending them to the previous class notes. So if you want to look at the scanned copies of these, you can check those, but you need to update them. All right. Bias-Variance Tradeoff. So let's say you have a training data in which you have three types of points, okay? Triangles, you have some circles, and you have some pluses, all right? So, and you're trying to draw surfaces so that you can distinguish between these 3 types of points. You can find out this surface. Then very complex. Right? This surface has a 0 training error because it puts every training point in the right area, right? However, and now the question is this the best answer that you want to get, right? Another solution could be which goes like this, just lines, okay? Now, of course, this solution has a lot of training errors, right? But the good, not the good thing, but one characteristic of this solution is that it is simpler, right? So this solution, the one that I denote with a straight line, is simpler but high training error. And the one that I denote with this curve is complex because it is, right? Because even geometrically, if you want to denote it, you would need a higher order polynomial, which means it's more complex, but it has 0 or very low training error. So the question becomes, which one do you prefer, right? If your objective was to minimize your training error, then you would have chosen this one, right? But what you really want is a classifier or a neural network which would do well in future. It would do well in the when you're testing it on unseen data, right? Which means that maybe 0 training error is not what you want, right? So if you go through some of the literature in learning theory, right, the statistical learning theory and machine learning theory, you will see that people have come up with statistical proofs which show that a complex algorithm actually would make more mistakes in future, okay? So we call those mistakes generalization error, which is once you have learned from your training data, now you actually apply it to new data. And the error that you get there is what we call generalization error. So what, yes, go ahead. What do you mean? No, that would be a different classifier. Here we are using neural networks. So here what we would do is we would just do the feed forward, and whichever class is giving you the highest O of L, you will choose that. So that is the prediction here. But that would be a different classifier. That's a good point. Anyway, so we actually want to minimize the generalization error, not the training error. All right. But the reason, but it is hard to do because we do not have that data to test yourself against, right? If you had all the data and if you had the labels from them, then why would you need a classifier, right? So how do you ensure that your classifier has a low generalization error, right? That is done by ensuring that your classifier is simpler, all right? So complex means bad generalization error, so I'm going to call it GE. Simple means better GE, okay? Now, I'm right now just saying this, but there are proofs that show that, right? But in general, there's a principle called Occam's razor, right? By William of Occam or Occam back in 13th century. The point behind Occam's razor is that if you have two solutions, right, both of them are giving you the exact same training error, then you prefer the simpler solution. Why? Because the simpler solution is expected to work better in the future. All right. So that is also known as, so trying to get a very low training error is also called overfitting, right? So you are chasing the data. Whatever data is telling you, you are sort of following it. So you do not want that, right? So in neural networks, there is a way to introduce the simplicity of the solution. So I'll maybe take 10 minutes in the next class to sort of wrap that discussion because we are out of time. But in general, you want to sort of look at this slide over the weekend, try to get a sense of it.